All right, welcome back everyone. My name is Dwight Duffy, and in this tutorial we're going to be taking a look at binary logic. We want to take a look at the actual truth tables that describe what computers actually do in terms of binary, zeros and ones. We know that a computer chip is nothing more than a collection of transistors etched into silicon that have input pins that can have either low or high voltage coming in and output pins, which is low or high voltage coming out. Everything that the computer does in terms of being able to do arithmetic, comparison, and everything else is embedded in little logical programs that are built out of transistors, built out of what we call logic gates. So we want to start with the very basic logic gates. There's actually just three that we need to look at. There's a NOT gate, there's an AND gate, and there's an OR gate. And we can create a truth table for each of these gates. These are the way that we know that the computer will behave given different voltages run through these different logical circuits. And these are very simple gates to create out of simple transistors. In the early days, the ENIAC computer used vacuum tubes, then later it was individual transistors, and eventually the transistors were etched into silicon. But you can go to Radio Shack and actually buy AND and OR gate chips and actually put together a circuit based on individual AND or OR gates. But in a modern processor, there are hundreds of millions of transistors etched into the chip. So we're just going to be kind of looking at the peeling back and looking just at the very sort of basic building blocks for building the more complex programs and circuits that make computers work. Okay, so let's talk truth tables. Not false is true. So 0, if it runs through a NOT gate, changes the low voltage into high voltage. Not true gives me a 0. So that's an easy truth table to complete. Now the AND logic is actually logical if you think about it. If somebody says you need this and this, if you need X and Y, then in order to get a true output, then you need to have both, which means really that the only true output will be if X is true and Y is true. Any of these other ones, like 0, 0 or 0, 1 or 1, 0, doesn't get the job done if it's an AND circuit or gate that you're running the electric power through. So 1, 1, so 1 and 1 or true and true gives me a true. So for the AND to be true, both X and Y have to be true. If somebody tells you you need to show up with a passport and a driver's license, then you better show up with both, right? X and Y if you want to be able to get through that gate. Remember, we're going to be doing this electrically just in a few minutes here. Now the OR, of course, we understand to mean that either one will get you through. So 0, 0 doesn't get you through, but 0, 1, because 1, the Y is true, so that works for an OR. 1, 0, that works. And 1, 1 is also going to work. Okay, so let's take a look at how we actually schematically note this. And this is using a program called Xlogic Circuits, which is a Java-based applet, and it's kind of stopped working on my computer because of the the signature, signed signature on the website that this is hosted at is not up to date anymore. So I'm not actively using it, but I do like the schematic, and I think this is a more common kind of way of looking at these gates. So you can see there's two inputs and there's two outputs. Power goes in these 2 bits. It runs through these logical circuits that we just described in the truth tables above. This little one here is a OR gate. The one that looks like a D, like my name, is an AND gate. The one with a little circle in the end, the triangle, that's a NOT gate. And then this is, of course, another AND gate. And this is actually called a half adder circuit. This will actually take 2 bits and add them up and give you a sum and a carry bit. And we'll actually take a look at this circuit in action here in a little bit. And then we'll come up with a truth table, which is the kind of the rules that govern how that particular circuit will behave. In reality, usually an engineer will develop the truth table first, meaning they'll come up with a little diagram with zeros and ones of what they want the chip to do, and then another engineer will take that truth table and figure out logically how to actually create, right, a circuit that will actually do that. So again, don't worry about the half adder truth table for the moment, but we will come back to that. But what we do want to be familiar with is kind of these symbols, and understand that this is sort of the idea here is this is what's inside the chip, and each of these logic gates can be implemented easily using transistors. And then you have power coming in and you have power coming out. It doesn't have to be a chip, but any microprocessor chip that does any sort of arithmetic operation is going to have lots of little programs like this built into the chip. All right, so let's get a drink of water here. Let's take a look at each of these individual gates that we described. Now here's the same circuit that we just saw, except instead of having those schematic diagrams, we have little chip blocks, and we've connected them all together, and we'll play around with these in a little bit later. But I'm going to come back over, and I encourage you to try these out. Go to Google and search for Logic Lab, and then look for the Nero Productions. As long as you're running Flash, you should be able to do this on a Mac or a PC. You should be able to test these circuits out that we just described in the truth tables. So input, I'm going to have a couple of inputs. Right now they're set at 0 because there's no voltage going to be coming out of these. And then I'm going to go to my logic ports. I'm going to grab an AND gate, and then maybe I'm going to come to output, and I'm going to grab an LED light, and then I'm just going to wire these up, connect one to the other, and now I'm ready to 0, 0 gives me 0, and that's what I expect with an AND gate. Remember, with AND, they both have to be on for power to get through the AND gate. So if I have 0, 1, flip this one on, it's still 0 coming out the other side here. Well, what if I have 1, 0? It's still 0. Because remember, with an AND gate, the only way to get out is 1, 1, and then that's going to give me the 0. Okay, I'm going to get rid of the AND, get rid of the light, go back to my logic port. This time I'm going to grab an OR gate, connect it up, a little temperamental. And I'm going to go to my output, and this time maybe grab a motor, just to show that it doesn't have to be light. It's the same idea, and I'm going to connect this up, power that, and let me turn both of these off. So with the OR, either one of these switches, sort of like the light switches in a house where you have two switches that can turn on the light, that uses an OR gate. Either one of these switches, will switch on the power. And that's the way I'd expect an OR gate to work. And if you switch them both on, unless it's an exclusive OR gate, just a normal OR gate, you're still getting power. And if we go back to our truth table, you can see the OR gate. If both are off, then you don't get any power. But if either switch is on or both switches on, you're still going to have true, or you're going to have power coming through the gate. So it's kind of cool to realize that you can build these gates, these logic gates, out of transistors. And this was the realization that this theory of Boolean logic had been around since before computers and even before electricity. But when electricity came along, people realized that it would be possible to actually create Boolean logic using electronics. And that was the basis for, and the premise for, creating the first digital computer, the ENIAC. All right, so we've done that, and it's kind of cool. If we come down here to the bottom, you can try all these different ports, and you can flip the AND. They both have to be on, to get power to come through it. And you can look at some of these other ones that are commonly used in computer logic. But AND, NOT, and the OR are the most common. Of course, false becomes true, or 0 becomes 1, and 1 becomes 0. It's just an inverter. All right, so let's go back now and kind of close the loop on this and see how, and I'm going to take a look at this first circuit that we looked at when we first started this tutorial. And we now see that we have these different circuit or little logical gates connected with 2 inputs and 2 outputs. And now I want you to imagine that we're going to be adding up 2 bits, either a 0 or a 1 added to a 0 or a 1, and we're going to get some result, which is going to be my sum, and then down here it's going to be the carry. And believe it or not, this circuit is called a half adder circuit, and it will actually do single bit arithmetic. So this is the type of circuit that's in pretty much every computer chip processor that's out there. So let's go back now to some theory that we looked at in the previous tutorial and just kind of remind ourselves how this actually works, so we can convince ourselves that this actually is a workable way to think about computer problem solving. So if I wanted to add up the numbers 6 and 4, assuming that I have that circuit, that half adder circuit. So 6 and 4 is actually a 4 and a 2, and then the 4 of course is a 4. And then we have a couple of zeros here. And remember the rules. 0 and 0. If we add up a 0 and a 0, we should get, and this is the sum, which is S, we should get a what? A 0, and their carry is 0, right? There's no carry. Actually, we don't need to write anything there, but there would be a 0 that would actually come out at that point. A 1 and a 0 is going to be a what? A 1, and we're going to have, again, no carry, so the carry would be 0. And a 1 and a 1 is a 0, because a 4 and a 4 can't fit, so we put a 0 here, and then we carry over to the 8. And we carry a 1 over here. So we'd have a 1 output for the C, or for the carry bit. And then we just add up the zeros here, and then we get 1. And 1, 0, 1, 0 is 8 and 2, which gives me 10. So 6 and 4 is actually 10. So we can use that same circuit all the way out for, right, as many bits as we want by just feeding the results from one cycle into that circuit again, right? For the next one, take the carry bit and use it to feed in to the next circuit. And there's a number of different ways that these kind of adding circuits are actually implemented, but the one we actually looked at schematically, like this, is a simple one. And so we can actually describe a truth table that describes how that circuit actually behaves. So again, if we come back over here, 0, 0 gives me an output of 0 and a remainder of 0. So S is 0 and carry is 0 if the X and the Y inputs, or the A and the B inputs, are 0 and 0. So if we went back over here, we would say, okay, the output is, the sum is 0, right, and the carry is 0. Now 0 and 1, if we go back to our circuit here, 0 and 1, notice gives me a output of what? 1, but a carry of 0. So S is 1, C is 0. So my S is 1 and my carry is 0. And I would expect if I went back and flipped these around, 1, 0 is still going to be 1, 0. So it's still 1, 0. And finally, if I have 1, 1, we flip both these on, so I'm adding up a 1 and a 1. We know that that's going to give me a result of a 0, but it's going to carry, the C bit is going to be a 1. So S is going to be 0, but the carry is going to be 1. So that would be S is 0 and carry is 1. So that's it. The truth table that describes how the half adder circuit should behave that we've reverse engineered from the circuit. And again, the way this would happen in the real world is somebody would come up with a truth table that would say, we want a computer chip that does this thing. And here is the truth table that describes how we want the voltages to work, the inputs and the outputs from the chip. And then from that truth table, we go back and design, using logic, a chip that will actually behave in that way. And that's the miracle of computers. The fact that the computer can run a machine cycle of billions of times per second, of course, is what really makes it possible in terms of the speed and performance and all of the dazzle that we see. But fundamentally, what the computer is doing is it's moving bits through little programs that are etched into transistors on the silicon chips. All right, so we've got truth tables for not, for and, for or, and those are like truths, like a religious truth, right? Those are immutable truths. And then we have truth tables that describe all the different sorts of operations: multiplication, addition, subtraction, floating point, comparison, all the different sorts of things that a computer should be able to do. And then in modern computers, we start seeing things like compression and encryption and camera circuitry and all those sorts of things actually built right into the actual chips. And that's what we've seen with things like the iPhone and Android processor, where we have lots and lots of different functionality built right into the chip, which means that we can have less chips, which means that the phones take less power and cost less to make and all of that. So in the early days, a lot of the PCs had tons of chips, and now we notice that the trend is toward more and more of that functionality getting built into a single chip or a small chip set. All right, so have some fun with the logic lab and see if you can duplicate this circuit and make it work. I use this little kind of branching thing in the extra spot in order to be able to take the power and sort of branch it, because if we look at the circuit here, we need some way to be able to take the power and have the power branch, and that's very common in a computer circuit to be able to do that. All right, that concludes this tutorial.